Okay, so when we were talking about specific heat capacity and the fact that energy was being added to a material and its temperature was going up, okay, we're dealing with thermal energy, obviously, but what kind of thermal energy? Kinetic thermal energy or potential thermal energy if there's a change in temperature going on? Kinetic, okay? Because as you increase the temperature of something, the molecules that it's made out of move faster, okay? So temperature is a measure of how fast the particles of a substance are moving, okay? That's how a thermometer works. When you put a thermometer into something, okay, energy is transferred to it by the impact of all the particles that are moving around. The faster they're moving, the more it gets hit, the more the mercury or whatever's inside goes up, okay? So it's a measure of kinetic thermal energy of a substance. Latent heat is potential thermal energy of a substance, okay? When I change the potential thermal energy of a substance, its temperature doesn't change. What does change? Think about this. If I have a block of ice and I start heating it up, okay? Let's say it starts at minus 30. Okay, I got ice at minus 30 and I start heating it up. I'm going to immediately start changing its kinetic thermal energy and its temperature will go up. But it'll only go up until it gets to what temperature? 0. Because once it gets to 0, it can't be ice anymore, right? And in fact, I can keep adding energy to it, but its temperature won't change. It'll stay at 0 because what is it doing? What does ice do at 0? Oh, please tell me you know the answer to this. It melts, yeah, okay. We live in Canada, guys. We have to know what temperature ice melts at. It's very important. It's going to be above 0, apparently, they say today. Okay? We might actually get some melting going on. All right? So it's going to start to melt. But that means that the energy I'm now putting into it isn't being used to change the kinetic energy anymore. It's being used to change the potential thermal energy. So now the molecules are moving as fast as they can in a solid state. Okay? Because they're still packed really close together, they can't move any faster than they're already going. But as I continue to add energy, the molecules will start to move apart. Okay? Because we know in a liquid, the particles of a liquid are always further apart than they are when that material is a solid. Everyone agree? Okay, so what happens when you change the potential thermal energy of an object is you make the molecules not move faster, but move farther away. Okay, and that's always what's involved in a state change. Once I melt all that ice, now I'll have water at 0 degrees Celsius. If I continue to add heat to it, the water it'll heat up, right? And it'll go eventually to what temperature? 100. Yeah, because at 100, it has to change state again, right? So once I get to 100, if I continue to add heat, the water will stay at 100. Okay, liquid water will not exist above 100 degrees unless you put it under extreme pressure. Okay, so it stays at 100 degrees, continues to boil, okay, and boil and boil. And what's happening to it as it boils? What's it turning into? Steam. Okay, the gaseous form of water, right? So again, the molecules are now, they're this far apart. Now they're moving even further apart, okay? Because in a gas, they're even farther apart. And when they're farther apart, they can move faster again, okay? As a liquid, they can only move so fast in the space they have, okay? And once they get to a certain point, they've got to get further apart in order to move faster, so they change state into the next state. The water will be at, it's not always going to be 100. At sea level under 1 atmosphere, water boils at 100 degrees. You won't be able to get liquid water above 100 unless you put it in a pressure cooker, and then you can get it above 100, which is why we use a pressure cooker, right? We can get the temperature up, okay? If you increase pressure, the boiling point of something goes up. If you decrease the pressure, okay, that's on atmospheric pressure, the boiling point goes down. That's why we said the other day, if you're on top of Mount Everest, you got to eat your itchy band while it boils because it's boiling at like 65 degrees, okay? There's not enough atmospheric pressure to keep it a liquid. Everyone follow? Okay. All right. And that happens if you go onto the surface. I think we said this. You go onto the surface of Mars, okay, even though it's like minus 30 to minus 100 and something, okay, if you were to walk out there without a suit, you would boil. Okay, because there's 1/100th of the atmosphere of Earth on Mars. There's practically no atmospheric pressure. It's like being in a vacuum. Okay, you walk out there and boil. Okay, it would be a bad way to go. Okay? I don't think it would be very much fun. All right. So what we got to look at here is the two different kinds of latent heat, because there's two different state changes. There's melting and boiling, okay? Or they're opposites, condensing and freezing, okay? But essentially, they're the same. All right. So this is the example we were using here just a second ago. We said we had some ice and we said minus 30, whatever, minus 25. If I add energy to it, which is what this graph is showing along the x-axis, okay, the amount of energy being added, if I add energy, does it look like it takes very much energy to heat ice to 0? Not very much, right? Like that's, what, very little right there. Okay, so we're not adding very much energy. It doesn't take much energy to heat to heat up ice, because ice has a very low heat capacity. Okay, the heat capacity of ice is 2.116 joules per gram degree Celsius. Okay, well, and while that's high compared to some things, it's low compared to others. Okay, so 2.116 doesn't take very much energy. Now, once I get it to 0 degrees Celsius, like we said, it cannot change temperature because it has to change state. Right? And so as I add energy to it, the ice begins to melt. Right? This is why when you make a snowball with your bare hands, your hands get so cold. Right? It's not that heating the ice or the snow to 0 takes a lot of energy from your hands, because it doesn't. But to change the state of the snow takes a lot of energy. Right? And the only place that energy can come from is you, which is why your fingers get so cold if you make a snowball without gloves on. Okay? Is that making sense? Okay. It's the same reason, guys, why ice can keep a drink cold for so long. Okay? If I throw ice into a drink, immediately the drink will transfer energy to the ice. Okay? And the ice's temperature will go up to 0, and then it'll stay there. Okay? And it'll continue to stay there until, as it absorbs more and more energy from the drink, okay? And then the drink's temperature will continue to drop, right? Because it's always losing energy to the ice. Okay? That sort of makes sense to everyone? Right, so that your drink stays right around 0 degrees Celsius as long as there's what in it? As long as the ice is in it. Once all the ice is melted, then it starts to get warm again. All right? But the ice will keep it cold as long as there's ice in it. Right? Now, obviously, it's colder near the ice. Like, if you're not stirring it, parts of the mixture may get, warmer than others. But in general, okay, if you kept it agitated, that's how it works. We're actually going to do that on Friday. Okay, we're going to take some snow now that we got lots of it. Okay, we can go outside and we're going to take it and put it in a beaker and just start. Just add some water to it, and you'll see that the water stays at 0 degrees Celsius until all of the snow has melted. It might not be exactly 0, but it stays at exactly the same temperature until all the snow is melted. Okay. All right, so latent heat, okay, is the heat that's involved, okay, in a state change. Right? We talked about how that was important for transferring energy from equatorial areas there in lesson 2. Okay, we said that when water evaporates from near the equator, it carries all the energy required to change it to a vapor to the new area and then releases it there when it condenses. Okay, now we're going to look at how much energy that might involve. Okay, now first we're going to look at, okay, latent heat of fusion, which is the energy involved in changing something from solid to liquid, or the energy given off when it freezes from liquid to solid. Okay. Right. The other one is specific latent heat of vaporization, okay, which is what's happening up here. Okay, it's the amount of energy needed to vaporize, change something from liquid to gas with no change in temperature, or vice versa, condense from gas to liquid with no change in temperature. Okay. Now, if I'm looking at this graph, and we call this graph the heating curve of water. I don't know why we call it a curve. There's no curve parts to it, but that's what it's called. Okay. We're looking at, again, the amount of energy being added, and then what's happening to temperature. So here, where the temperature is changing, if I wanted to calculate how much energy that took, how would I do it? Let's say I know that it's ice. Easier than that. It's what you've just been doing. What have you just been doing? What formula have you just been using? Right. Okay. E equals mc delta T. Anywhere where temperature is changing, I should be able to calculate the energy involved because I know the temperature change and would probably know the mass and the material. Agreed? So anywhere on this graph where the line is going up, the temperature is changing. So I have to use a formula that involves temperature change. Okay? So I could calculate the change in temperature right here right here, or sorry, the change in energy, sorry, right here, and up here as well. Right? So if we were saying, let's say that this was 100 grams of ice, okay, and I wanted to calculate how much energy was involved right here, I would just go 100 grams times times 2.116, because it's ice, right? Ice's heat capacity is 2.116, and it's going from minus 25 to 0. Okay, so now I would have the amount of energy required to heat the ice from minus 25 to 0. Everybody all right with that? Okay, this formula will not work here, because it'll tell you the energy is what? 0, because the temperature change during that section of the graph is 0. So obviously that's not good. Okay, we need a different formula. Okay, and what we're going to use, okay, is this formula right here. Okay, and this is in your notes, by the way. Okay. E equals mLF, and LF is the latent heat of fusion. Okay, for water, that's 333 joules per gram. Okay, so if you have a gram of ice, which isn't very much, that would be a very small ice cube. Okay, a gram of ice, it would take 333 joules to melt it if it was sitting in your hand. Okay, that's why it always feels so cold when you grab onto snow or ice. It takes a lot of energy to melt it. Okay, your average snowball is probably, what, 100 grams? Okay, something like that. When you make a snowball, about 100 grams worth of ice, okay, packed in there. Well, think about it. That's a lot of energy that has to come from your hands if you were to melt the whole thing, hold it in your hand till it actually all melted. Right? So it's not hard to see why you would get such cold fingers. All right, so now, if I know that the energy is equal to mass times latent heat of fusion, I should be able to calculate how much energy would be involved in now melting my 100 grams of ice that I just heated to 0. Okay, is everyone following me there? Okay, so you're never going to have to manipulate this formula. You're always just going to use it like this. Okay, so I would use that part right here. So like we said, this part here would be E equals mc delta T. This part right here would be E equals mLF. All right, so the big thing to realize here, guys, is that changing kinetic thermal energy is easy. Changing potential thermal energy is very hard. Okay, it takes a lot of energy to change the state of something. Okay, way more than it does to change the kinetic energy of something. All right, so that's kind of what we have to get out of this. All right, especially when we are linking it back to how much energy can be transported in a moist air mass, okay, from the equator to a more northerly region. Okay, all right, so now after I've added in however much energy I need to add, which would be 100 times 333, okay, so 333,000 joules. It's kind of a lot. Okay. Sorry, that's not right. I can't multiply this morning. Okay, 333 times 100 is only 2 more zeros. 33,300 joules. All right, and then for this one here, we said it was 100 times 2.116. We might as well just calculate it since we're doing it. Okay, so 100 times 2.116 divided by, or not divided by, multiplied by 25 degrees. All right, is that a pretty major difference? It only took just over 5,000 joules to heat the ice from minus 25 degrees to 0, but it took 33,000 joules to melt it. Right? State changes require lots of energy. All right, so I've done this step. Now I've melted the ice. Now what do I have? Water at what temperature? 0 degrees Celsius. All right, I keep adding energy to the water. The water's temperature is going to go up. Yeah, all right. So if I start here and I keep adding heat, how much is the water's temperature going to go up by? Stephen, how much will it go up by? 100, because that's the temperature water boils at, right? If I keep adding heat, the water's just going to get to its boiling point. So, okay, the temperature is going to change from 0 to 100 degrees. So can I use this formula right here to calculate how much energy would be required for that step? I can, because I know the mass. We've said it's 100 grams. We know now it's water, so that I have to use the specific heat capacity of liquid water now. And the temperature is changing by 100 degrees. Okay, so we'll have our 100 times 4.2 times 100. Okay, so 42,000 joules, okay, to heat water from 0 to 100 grams of water, okay. Okay, now I've got liquid water at 100 degrees Celsius, and it is probably now at a rolling boil. Okay, that's the kind of boil where it's bubbling all over the place. Okay, so it's boiling and boiling and boiling, but it's staying at 100 degrees Celsius. So now I'm in this section of the graph, and I'm changing liquid water into steam, okay, or gaseous water. Now, to change liquid water into gaseous water, I use not the latent heat of fusion, because that talks about the change from solid to liquid or liquid to solid. Now I need the latent heat that involves changing from liquid to gas. Okay? To change 1 gram, that's 1 milliliter of water, from a liquid to a gas at 100 degrees Celsius requires 2,260 joules of energy. Okay, that is a lot. So can an air mass carrying moisture evaporated from the equator be carrying a lot of energy? Because I'm pretty sure it's got more than a couple of grams of water in it. Okay, when we get a big heavy rainstorm, think about how many liters of water falls. Okay, it's a lot of energy stored in that evaporated water. Okay, so the hydrosphere plays a big role in transferring energy, and the jet stream that we talked about yesterday, okay, is also a major tool in forcing those air masses to move, okay, and bring them places to bring that energy along. Okay, so we got our 2,260 joules. So we've calculated all our energies up to this point here. We had 5,290. Okay, for this part we had 33,300 joules for this part, and this part was 42,000 joules. Now we ought to be able to calculate that part with this formula: E equals MLV. All right, and LV is this number. Okay, 2,260 joules per gram. Okay, so E equals mass times the latent heat of vaporization. So 100 grams times 2,260 joules. Okay, so that's going to mean we're going to add 2 zeros onto that. Okay, so we're going to have 2,260,000. Okay, 226,000 joules. Okay, in order to change the temperature, or sorry, not to change, in order to change the state of 100 grams or 100 milliliters of liquid water. Okay. When you get out of the shower, do you feel cold? Why? Weren't you just standing in some nice warm water? What's happening to the water as soon as you get out of the shower? If you just stood there, okay, would you eventually get dry? So what's happening to the water? It's evaporating. Where is it getting the energy to evaporate from? You. Okay? It's getting the energy to evaporate from you. Okay? That's how sweat works. Okay? When you work out and you get hot and you start sweating, it's not just inconvenient and gross. Okay? It's helping to cool your body down. Right? Because as you cover your skin with a thin layer of water, okay, and that water begins to evaporate, for every gram of sweat that evaporates off your body loses 2,260 joules of thermal energy. Okay? You can get cool in a hurry, okay, with sweat. Agreed? Okay? Now, If you're sweating, but you're just standing still, is that going to work very well? No. If you want to get cool faster, oddly enough, you need to move around. You need to get air moving across all the liquid that's on your body in order to make it evaporate faster. Okay? Sometimes you sit in front of a fan. Why does a fan make you feel cooler? Because it increases the rate at which the evaporation of your sweat happens. Okay? And so you cool off faster. Okay? That's why a fan or wind, okay, if a little breeze comes up, it kind of feels nice on a really hot day. Okay? Because it helps to evaporate that water a little more quickly. Okay? But that's also the reason why we want to dress in layers if we're going outside and doing something physical on a very cold day. Okay? Because if you start getting hot and you start sweating under your big heavy coat, as soon as you stop your activity, you're going to get cold really fast. Okay? Because generally, cold air, right, can quickly take up moisture off of your body. Right? And so when that happens, okay, you're losing your energy a lot faster and you're getting really cold and you can get hypothermic really fast. Okay? So you always want to dress in layers so that as you work, you can take layers off and not get too sweaty. Right? Or at least control your rate of evaporation, okay, a little bit more. Making sense? All right, so we've calculated now all of these things. Now, if I've done that and I've evaporated all the water, what do I have now? I have a whole bunch of steam, 100 grams of steam, okay, at 100 degrees Celsius. If I start heating the steam, what will happen? Probably never thought about this because it's not something we normally do, okay? But if you heat steam, will its temperature go up? Yeah, just like anything else. Okay, well, steam has a different heat capacity than liquid water does and that ice does. Okay, water's weird that way. Okay, every state of it has a different heat capacity. Okay, so I could calculate how much energy would be required, let's say, to heat it to 125 degrees. Okay, by using E equals mc delta T. All right, and I would plug in my numbers again. So I would have 100 grams times the specific heat of steam, which is 2.2, is that right? Someone just 2.02. Okay, joules per gram degree Celsius times 25 degrees. All right, so 100 times 2.02 times 25. All right, so 5,050 joules to heat the steam. All right. Is that looking like a lot of energy to take ice from minus 25 and turn it into steam at 125? Yeah, it's kind of a lot of energy. Okay, it would be like throwing an ice cube onto a hot pan, right? You'd watch it dance, okay, for a little bit as it quickly raised in temperature, melted, and then okay, it would take a little while, obviously, then to get it up to boiling and evaporate it all. Should you ever boil away all the water in a pan? Never. Okay, you'll do it once by mistake at some point in your life, okay, and you'll know as soon as you've done it because the whole house stinks like burning metal. Okay, because whatever minerals are in the water burn onto the pan. Okay, and it's almost impossible to clean off. Okay, it's disgusting. All right, everybody with me here? Is this making some sense? Okay, so here's how you're going to get tested on this. You're going to get a problem that's going to say you have 250 grams of ice at minus 10 degrees and you want to heat it into liquid water at 30 degrees. Okay, so you'd have to look at your heating curve. Okay, bigger version here. Okay, so you'd have to look at your heating curve and go, okay, I'm starting here and I'm going to here. How many steps is that? 3. I've got to heat the ice. I've got to melt the ice. I've got to heat the water. 3 steps. All right. Anywhere where the line is going up on this graph, you use which formula? E equals mc delta T, because temperature is changing. You can't use these two. Okay. E equals mLF and E equals mLV can only be used here and there. Okay. Everywhere else it's E equals mc delta T. There's no manipulating. All you have to do is find the energies and add them up. Is that very difficult? But you know what? A question like that would be like a 6-mark question just because there's lots of steps. Okay, the steps are easy, so they're kind of gimme marks really. Okay, so on a unit exam, when you get that question, and you will, okay, make sure you get all the steps right. The only trick is remembering that, sorry, there's 2 tricks. You got to remember that I use MLF at the freezing point. That should be easy. Okay, and I use MLV at the vaporization point. Okay, the other trick is remembering which specific heat capacities to use. Okay, you got to remember that down here you use the heat capacity of ice, here of water, and here of steam. Okay, sorry, there's 3 tricks. And this isn't a trick, but it's just a mistake that people make. What's delta T if I want to heat ice from -10 to water at +30? See, that's the mistake people make. There's 2 separate temperature changes. I can only change the temperature of ice by what? 10. Okay, but a lot of people will plug that 40 in because they look, oh, it goes from -10 to 40. Okay, or if they're using, and they use it in every step. Well, you didn't change the temperature of the ice by 40. Okay, you changed the temperature of the ice from -10 to 0, which is only 10 degrees. Okay, so that's a mistake that sometimes people make. We want to make sure we avoid. Okay, all right. Okay, so we've talked a little bit about this. Why does putting ice cubes in water make your drink cold? Okay, so you might want to just jot down a little bit about what we talked about there, about how ice obviously doesn't take much to change its temperature, but it can absorb a lot of energy while it's changing from solid to liquid. And that's why it can keep your drink cold for so long. It can continue to absorb a lot of energy as long as it's in a solid state, okay, while it's melting. Okay, we just talked about sweat. Okay, our bodies naturally sweat, and it takes energy from our body in order to make that evaporate. If we're using energy to evaporate the water, we're going to feel cooler because we're losing energy. All right. Now, does it work better if you are like an excessive sweater? Okay, like if you sweat a lot versus like perspire. Okay, does it make much difference? Is it more efficient to sweat more? The answer is it's not really. You just need a thin layer of perspiration on your skin in order for it to be effective. Okay? Some people sweat more than others. Okay? It's just a natural thing that happens. But it doesn't necessarily mean that they're cooling their body any better. Their sweat glands just work faster, okay, than others. There was a Nikolai Habibulin, used to be a goaltender for Chicago and for Edmonton, and he kind of bounced around a bit after that. He sweats a lot. He used to have holes drilled in the bottom of his skates to drain the sweat. Okay, they actually caught it on the crease cam once. Okay, he was standing there and you could actually see the water dripping out of the bottom of his skate. Okay, he would come in. He would have like 6 or 8 pairs of blocker and catcher, okay, for every hockey game, because he would come in at the 10-minute mark of the first period and go and just throw them off, and they would just be dripping, and he'd get a fresh set. Okay, go back to the crease. Okay, he's just a guy that just sweats a lot. Okay, that's why Edmonton always lose. Okay, they always lose. I'm an Oiler fan. I got to say that they always lose, but they lost a lot in their shootout. Okay, because their goalie was getting cramps by them because he'd lost like 10 pounds, okay, worth of water over the course of the game. Okay, so the strategy was always try and get him to the shootout, because they know Habibulin would be just dog tired by then because he'd have lost 10 pounds worth of water. Okay, is it healthy to lose 10 pounds worth of water? No. Okay, that's why he was always going back for another water bottle. Okay, you got to keep hydrated if you're losing a lot of that moisture. Okay, gardeners often spray their crops before a frost. Okay, so if especially if you're like you're growing apples, like you have an orchard, or grapes or things like that, and there's going to be a really like a light frost or something like that, you don't want that to happen, because if that happens and your fruit freezes just a little bit on the outside, nobody will want it because then it's all squishy. Okay, so what they do is they turn on their irrigation and they spray it so they get a very fine layer of water on the outside of the fruit. Now when the temperature drops, the water on the outside of the fruit freezes. And when it freezes, what happens to its energy? If you're changing state from liquid to solid, are you giving away energy? Where does it go? It goes into the fruit. Keeps the fruit from freezing. Okay? So the water on the outside freezes, and as it freezes, the energy it gives off during the change in state, some of it goes into the fruit. And that can keep the fruit from freezing. Okay? And that preserves the quality of the fruit. It's only good if it's going to be a very light frost. Okay? It would save like maybe tomatoes and apples and things like that. If it was going to be a heavy frost, everything's toast anyway. Okay? If it's going to drop to like -6 or something like that, it's not going to do any good. Okay? But for a light frost, it'll work. Okay, in a cooler, we always put ice in a cooler. Okay? And up until now, you're probably just thinking, well, ice is cold. That's why I put it in the cooler. Well, you know what? Ice in the cooler is at what temperature? 0. Because as soon as you put it in the cooler, it starts to melt. Okay? So the ice that's in the cooler is not necessarily all that cold. The reason you put ice in the cooler is it can absorb lots and lots of energy while it melts. Okay? Does that make sense? You wouldn't fill the cooler with water at 0 degrees Celsius, okay? Because the water would warm up almost right away. Okay? You've probably seen that happen if you've had a cooler and all the ice is melted. Yeah, everything in there is no good in a matter of a few hours once the ice is all melted. As long as there's some ice in there, though, it stays very cold. All right. Tomorrow, okay, we'll work on these latent heat problems. Your quiz tomorrow is not going to happen. Okay? You should be starting to study for both unit and final exams. And, okay, you've got your climatograms that need to be done for the 8th. Okay? So make sure that you're getting those done as well.